the nodes, right? We have to visit all the nodes. We could also talk about doing an in-order traversal, but actually for counting, it doesn't even matter, right? It doesn't matter whether we're going in which particular traversal order. As long as we're visiting all the nodes, we can get a count, right? So what's our algorithm going to be? How are we going to think about this recursively? I start at the root. I come here. Now what? Anybody?
Are you trying to count every node, or are you trying to count on one
I'm
side?
counting all the nodes. I'm doing size in essence, right? So how do I think about it? I follow the root. Is this null?
No, so you move to the left.
So count it, right? If it's not null, count it, increment something, increment a counter, right?
Oh, so you do that for left and right until it's null, you add the two.
Then I go to the left, and if that's not null, I count it, right? And then I go to the left, and if it's not null, oh wait, this is null, so I don't count it. I just return. Now I'm back to here. Now I go to the right. Oh, that's null. I don't count it. Now I'm done with both of this sides of the tree. Now recursively, I'm going to be back to here. I'm going to go to the right. The right's not null, so I count it, right? I go to the left. The left's not null, so I count it. Then I go to the left. Oh, wait, the left is null. I don't do anything. I come back here. I go to the right. Oops, that's null. I don't count it. Now I return to here. Now I go to the right. This is not null. I count it. I go to the left. That's null. Don't count it. Come back. Go to the right. Not null. Don't count it. I incremented 1, 2, 3, 4, 5 times, and I have 1, 2, 3, 4, 5 nodes. Make sense? This one's a little harder, right? It's a little harder because now we got to think about returning something, right? We're going to have to think about returning something. So let's see if we can figure out how to count all of the nodes. Okay, how do we count the nodes? So let's see if we can do that real quick. Let's do public int count nodes. And I'm going to, again, you don't want to pass it anything. And of course, I'm going to have to do count nodes starting at the root. So as always, you're going to have a private one that looks just the same, right? That is called the same thing, but it's going to need one more piece of data. In this case, it's a binary. You're going to need to tell it where to start that. Oops, not what I wanted. Binary entry search node called start node. Okay. I'm going to have to return an integer. So how do I do that? How do I say if I'm null, if I'm not null, then count me? What's the code? Or let's say if I am null. If I am null, we're done, right? So the base case is you ran out of road, so go back. How do I say that?
If start node equals null, then return 0.
Right? Don't count me, right? Return a 0. We're counting, so we're going to have to return numbers here, but return 0. There's nothing at me or anywhere below me, right? 0 is the sum of everything from me down, right? Otherwise, I need to count me, and I need to then count my children, right? So how do I count me? I'm going to return what? 1 for me, right? And you got to go count my children now. With what? What parameter?
The start node.
Just with start node?
Dot left, and you'd probably want to add plus start node dot right.
Right? And then here, of course, I've got to return whatever came back from that whole thing. If you run off the road, there's no more nodes below me, so just count 0. Otherwise, return 1 plus whatever the count of my left whole tree is, plus whatever the count of my whole right tree is. And then each one of those will do the same thing recursively on down the road. Okay. These things look weird to the eye, right? When you see them, they look weird. You might look at them and go, how does that actually do any work? How does that bit of code actually do anything here, right? It seems so odd when you see it. But I promise when we go to main, if I now say sysout print, and I'm going to print not args, but let's say nodes, right? I'm going to say maybe count equals, and then I'm going to count my ints dot, and then I'm going to call count nodes. So if I now run that, 1, 2, 3, 4, 5, 6, 7 should be 7 nodes, 7 nodes. There we go. Okay. So the recursive thinking is different, right? It's different, it's interesting, but the more you do it, the more you practice it, the better you'll get at it as you think through these scenarios. What is my base case or base cases? What happens if I run out a road? Is that a sign, right? Because now we can walk forward with some other ones. For instance, if we want to do an in-order traversal, right, where it's not that we just want to count the nodes, maybe we actually want to build a string that contains the data from all of them, or maybe we want to print them, right? How can we do an in-order traversal? And that would be our next challenge. It's really no harder than what we've done here. You visited all the nodes. You just need to make sure you visit them in the right order. Here, we didn't really care. We said, count me and then go count my children, right? If we want to do an in-order traversal, we have to do it in the correct order, right? We can't just be cavalier about that. So then you have to say, wow, first I have to go to the left, then I have to deal with me, and then I have to go to the right. So once you get that thinking going and get those base cases, you can start writing these things. So one good way to move on from this point would be write a method, for instance, that sums up all of the nodes instead of counting them. Try to see if you can write an in-order traversal that prints out the tree 1 item per line, right? See if you can develop something that returns a string that contains all the data from the tree with commas in between them in an in-order traversal, right? These are the kinds of things that now you can start pondering and start figuring out whether you can write these recursive things from scratch, because they are hard at first, right? They are hard to write. But they're also, if you look at these, extremely elegant and small, right? They do a lot for a tiny, tiny bit of code, right? There's not much here, right? In fact, you could argue, you could even write this in a ternary operator, right? You could write this whole thing in a ternary operator, and therefore, yeah, that could be cool too, right? You could write a single line and that does all of the counting for the tree with a recursive call. So anyway, we're running out of time here, but that was a lot of interesting stuff. I can certainly give you this code. I don't know whether you were trying to keep up or not, but I can